We are starting to talk about the applications of exponential functions, and specifically in this video, we're going to talk about interest. So, interest is is money that you earn on your money. If you put money in an account that earns interest, how much money will you have in a certain amount of time? Well, we can figure that out, and we can do so systematically. Like if we start with $10 and earn 5% interest each year, how much money we would have after 3 years? Well, the way it works is this. After the first year, or during the first year, you start with $10 and then you make 5% on that $10. So 5% of $10 is 50 cents. So you would make that 50 cents in that first year. Now you start that second year with not the original $10, but the $10.50 that you ended year one with. Then you would multiply that $10.50 by 5% or 0.05, and then you'd add that amount, which is like $50 and 0.25 cents, or no, 50.025 cents, and you'd add that to your 1050, and you do that until you end up with, after year three, you end up with $11.57.65. And so interest doesn't just get you one payment, right? If you keep it you get interest at each like payment interval. And for this situation here, this is what's called simple interest. And so this equation, this A equals P times that value times the quantity 1 plus r to the t power. This 1 plus r is essentially the base of an exponential function, and we've talked about what that looks like. T is the number of times, is the amount of years you have your interest, your money in the account for, basically, and then P is what you started with. A is the final amount. Okay. Now, there's a little more to this, right? If we look at this equation, it doesn't look as simple as we're used to seeing when we talk about an exponential function. And so let's break this down to see if we can identify what these letters represent as far as how it mirrors something like f of x is equal to a to the x, or let's do b to the x, like a b base to the x. Okay. So like what this is, right? If I really think about it, there is a coefficient to this b right here. Okay, it's 1. And so that's like what p is. And so it's an initial amount that we are going to apply like an exponential growth model to. And p, like, so everything essentially is just scales up, right? This p in a function is what we would multiplying all the outputs by. So it's a scaling up. So instead of something going up by 1 every time or whatever, or instead of something starting at 1, it would start at whatever value we wanted it to. And it would kind of have a more drastic growth in that way. So that's not different. It looks different here. And then this 1 plus r is like analogous to the b. And we know that if b is greater than 1, that is a growth. Because we'd have numbers greater than 1 and be raising them to increasing powers. And so just get larger and larger. If b is less than 1, right, but greater than 0, right, if it's between 1 and 0, then we have decay. We have the opposite of growth. Something's getting smaller every time. That's like, for example, a number between 0 and 1 is 1/2. And so 1/2 to increasing powers just gets smaller and smaller. And so by changing this value of, well, r is just a rate, right? And rate, when expressed as a decimal, is usually, it's a very small number. It's like for example, 10% is just 0.1. And so if you change this plus to a minus, what you're doing is toggling between these two scenarios here, okay? And that will result in either your growth or decay, but the equation essentially is the same thing. Things that depreciate over time are like your assets. So um, things like cars, uh, a property that doesn't gain in value over time. So like, I mean, cars is really like kind of the best example of that, but other things also lose value over time. Okay. Now, there's more to interest than just what we've seen so far, because there's something called compound interest. And in this scenario here, it essentially is compound interest. It's just that it only pays you one time each year. Now, you could have compound interest that pays you quarterly, for example. that doesn't mean that you earn 5% interest every 3 months, because a quarter is 3 months. It means that you earn a quarter of that 5% interest every 3 months. But because it's compounding more often, that second quarter, you're good. That 5%, that portion of the 5% that you're going to be earning in the second quarter is going to be on more money. And so that if that what that does in effect is it earns you more money over time. And so we have this equation here. This is the compound interest formula. Okay, and this is a very famous formula. It's used all the time, and in financial markets especially. Like, this is how we can kind of not predict, but like calculate how much money we'll have if we're guaranteed a certain interest rate at a compounding interval. And so a common compounding intervals are like, well, yearly, that's if n was 1, or quarterly, that's b n is 4, monthly, n is 12, and then there's other ones too. So let's try to use this formula to solve a problem here. We want to know how much money will you have after 5 years if you start with $250 and you compound annually at 7%. Well, you would, so I'll just write it out. The amount we're trying to find, is equal to the initial amount we started with, $250, times 1 plus, and then R is 7%, so that's 0.07, divided by the number of times compounding. So in this case, it's just 1 times, and then n again is 1, and we're doing it for 5 years, so times 5. So this would be 250 times 1.07, right? I just cleaned that inside part up, to the 5th power. And when you multiply that out, you should get $350.64, which it seems kind of like a lot of money. That's a pretty good amount. 7% interest rate is pretty high, so it makes sense that you would earn a little over $100 in 5 years. So for those kinds of compound interest problems, when you're trying to calculate the amount of money you'd have after a certain amount of time, if you started with some money and you had some interest rate, those kind of problems, the math is all basically the same. And it's just a matter of interpreting the problem and reading what the compounding interval is and putting it in the right spot and solving the problem. There's a little more to it. There's some questions, and we'll get to those later, where you have to actually solve for a different variable, a different one other than a, and it does make things a little more difficult, but it's still totally manageable when we're using exponents. But what I want to look at now is, what effect does increasing the compounding interval have? So, for example, like if I were to compound daily or hourly or something, how does that impact? Like, would it be? I think it's safe to assume that it'd probably be better, but how much better? See if we can somehow quantify this. And the way we're going to do it is look at a very simple example here. What if we said, for the sake of this, that p was equal to 1? So we started with $1. We said the interest rate was the best, like a great scenario was 100%. Okay, 100% interest rate. And then we just want to look at 1 year's worth of interest here. So t would be 1. Well, what we would have then, if we just simplified that, a would equal 1 is p. So the inside would be 1 plus 1 over n to the power of n, right? Because t is 1, so that's 1. That's all just like that. Now let's look at it. Let's make a quick table here and see how this works. So let's say this is n. This will be our number of times compounding, and then this is when we plug in n into this little expression here, and we evaluate and see what it equals. So if we just look at 1, right? If we plugged in 1 here, it'd be 1 plus 1 divided by 1, which is 2, to the first power. It's just 2. Okay, so that's great. I mean, it makes sense too. If we just earn 100% interest one time per year, we double their money. If we said, all right, what if it compounds twice a year? Well, now that would be, it'd be 1.5 squared, which ends up being 2.25. Okay, if we made it 4, if we plugged in 4, that'd be 1.25 to the fourth, which is 2.441463. Using a calculator for this, I can't do anything like that in my head. If we said monthly, so if we said the compounding interval is monthly, that would be 12, right? So n would be 12, and we plug in 12, we get 2.6 1.13. So that's great. I mean, we're making now, right? We started off by doubling our money. Now we're like doing significantly better than just doubling it. If we increase it more, like say it's every day, 365, that would be 2.71456. If we made it, if we multiply 365 by 24 to do hours, that's 8,760 hours in a year. There's 2.7181267. What if we wanted to go a step further and make it minutes? Well, there are 525,600 minutes in a year. I'll let that one sink in for a minute. And that would give us 2.7182792. And then if we even went even crazier and we said, all right, what about seconds? So we multiplied this 525,600 by 60 seconds. There are 31,536,000 seconds in a year. So that's 2.7182. It looks like these numbers are getting really close to each other. And what we're doing here is we're increasing values for n, right? We're getting larger and larger. Effectively, it's this. We're familiar with limit notation. The limit, as n approaches a really big positive value, like infinity, of this 1 plus 1 over n to the nth power is equal to something that looks like this. In fact, it is this. It's actually there's a very special letter that we use in math to represent this value, and that letter is E. And E is Euler's number. It is a number that was discovered when studying this exact situation here, when studying the best possible case when it comes to compounding interest. And it is used, and it comes up all the time in math, and it's kind of like the Illuminati. It's like this thing that just shows up all over the place. So in the event we had what's known as continuously compounding interest, like not only is this thing compounding every second, it's compounding literally every instant. Okay, what we get is this simplified formula that you may have heard before, and is sometimes called APERT. And it represents continuously compounding interest, or just continuous growth. And E again is Euler's number, okay? But the math is actually simpler here, because now we don't have to worry about that 1 plus 1 over n, or that 1 plus r divided by n, like base. The base is just E. And E is really easy for us to do because E is a button on every single calculator, or at least every single scientific calculator. E is so common it has its own button. And so the math is real simple here. Let's look at an example of using continuously compounding interest. Okay, how much money will you have after 5 years if you start with $250 and you're compounding continuously after 7%? First of all, the way you know how to use APERT instead of the other one is the word continuously. So if you're being asked an interest question and you see the word continuously, that's APERT right away. Okay, if it doesn't say continuously, it'll say something like compounded at some other interval, like monthly or yearly or something. So this is really simple. It's APERT. A equals P times E to the RT power, right? It's just E being raised to the RT power, not the P. So then we just plug the numbers in. We started with $250 times E to the interest rate is 0.07 times T is 5, and that equals, I already have the answer down here, it's $354.77. Now we asked a very similar problem at the start of this video where we were compounding annually, right? Or no, we were compounding, I can't remember what is quarterly or annually. But if you go back and look, you'll see that this value is higher than the other value, which is great. I mean, that gives us more money. That's the optimal scenario there. It's not super realistic. This doesn't really happen in banks and stuff. Like, you don't get continuously compounding interest. But in any case, that is the ideal scenario.